Welcome back to the Tech Civil Learning. My dear friends, just give me your 20 to 30 minutes time. You'll surely going to understand the concept. At the same time, I hope that you have seen the previous video, that is analysis of flange beam, so that you can understand this concept very clearly, right? If you have not gone through that once, so it will be very difficult for you to understand the concept. So hope you have gone through that video. So without wasting time, let's understand the today concept, or let's design the L sections. Here we need to design L sections. My dear friends, I have told you that L sections are generally seams at the what you call end point of the constructions, right? When we can say that like the T beam is intermediate type of beam, L is the end type of beam, right? Generally L type of beam is seams at the end of the slabs and the support. So hope you have understood the previous video. So here in the data it is clear span is given, right? Thickness of flange is nothing but the thickness of slab is given, live load is given, spacing of beam is given, M20 grade of concrete is used, and HYST bar, that is 4415 is used. So and the what we call width of the support is given as 300 mm. So here what I need to tell you that the design steps of the T beam and L beam is same. There is a little difference that in L beam we need to find out the bending, torsions and the shear force, as it is lying at the support, right? And you know that at the support all these criteria are acting sufficiently. So we need to calculate all these things very clearly. So all these things are only the extra things which you need to which you need to designs, or which you need to find out, else everything is same. So let's understand. The first thing is we need to calculate the effective depth as usual. So effective depth for the simply supported beam should not be less than or should not be greater than L by 20. So I have taken L by for the simply supported beams the effective depth should not be greater than L by 20. So I have taken L by 12 to L by 15. So into span is nothing but the 8 meters. So I have converted into mm. So 8000 mm. So ultimately the value comes 6.66 66.67 and the 533.33. So from that ones I have taken the round of value as 700 mm. You can take it 650, you can take it 670 depending upon your requirement of the design. So I have taken as 700 mm as usual of the T beam. So here overall depth we need to calculate. As you know, overall depth is nothing, just imagine if this is L sections, right? If this is L sections, right, and here the reinforcement is provided, then the distance from the topmost fiber to the bottommost fiber is nothing but the overall depth, and effective depth is the center of this reinforcement to the topmost fiber. So we can say that for the overall depth, that is effective depth, that is depth up to here, right? Depth up to here from the topmost fiber, and this one is nothing but the clear covers. So clear covers we have to assume as per the atmospheric agency. It is given in page number 47 of IS codebook 457. So from the codebook IS 457 I have taken as the clear cover 50. So overall depth will be 750. Right, so hope you understand. So let's calculate the width of weave. That width of weave is nothing but this width, right? So how much will be this width? So this means for the width of weave, the formula is given 1 by 2 to 1 by 3 of the D. Here D is nothing but the effective depth. So we have to 1 by 2 into 700. Sorry my dear friends, here it will be 700 and here it will be 700. So if you calculate 1 by 2 into 700, it will be 750. It will be 750 and it will be 233, right? 233. So from these ones I have taken as 300 as the width of vertical weave, or we can say the width of reeve. So similarly I will calculate effective spans. Effective spans formula is given in the page number 34 of IS codebook. So let's move to the page number 34. So the effective formula, we can calculate the effective span, so the effective length in the two way. Let's move to the page number 34. Yes, we are in page number 34. So my dear friends, as here it is said the effective spans of the members is not built integrally with its support. So it can be calculated as clear span, and clear span is already given in the questions, plus effective depth, and we have already calculated the effective depth. So clear span plus effective depth will give you effective span and or the slab or beam or means center to center of the supports. Else you can calculate it also by center to center of the distance, right? If it is beam, right, suppose randomly if it is beam, and if this one is support, right, if this one is support, then center of these ones to the center of these ones, right, sorry, center of these ones. So this one is 8 and this one is 400 something. So let's move to the question. So here the center to center of the support, so clear covers, and the supports means what you call width of support is given 300 mm. So 0.3, it means 300 mm, right? So 0.3 plus 0.3, right, divided by 2 will give you 0.3. So center to center of support will give you 8.3. Similarly, clear cover plus depth. Clear cover is 8 and depth is 700, right? So that will be 0.7, right? It will be 0.7. So ultimately it will give you 8.7. So from these two ones we have to take the least value for the effective span. So the least value is 8.3. So hope you understand the steps 1. My dear friends, if you have any doubt, then please put it in the comment sections. And if you really like the video, please don't forget to comment. So in the second steps, we will calculate the effective width of flange. Right, its formula is given in page number 36. So you prefer page number 36. From there you will get the BF formula, that is effective width of flange. So BF formula will be given as LO by 12 plus BW plus 3DF. So LO is nothing but the L, right, and L distance is nothing but the effective length. Effective length is 8.3 meters. So 8300 in mm by 12 plus already we have calculated width of weave is nothing but the 300. DF is already given in the questions. So ultimately you will get 1442 mm. So other way to calculate effective, sorry, means what you call effective width of flanges means what you call 300 plus adjacent means center to center adjacent of slabs. So it will be 0.5, right? So 300 plus 0.5. So as 300, it will not be 300, my dear friends. It is given 3 meters in questions. It is given 3 meter the spacing, right? So 3 meter plus 0.5, so means 3.5. So 3.5. While you convert 3.5 into mm, it will give 3500. So from these two ones, we have to take the smallest value or the least value. So 1442 will be the effective width of flange. And hope you know why we are taking effective width, as I have already explained. So if this one is L section, so this one is the effective flange width. This one is F, means what you call effective depth, right? If from here to here is the overall depth, right? So this one is the means depth of flange. So as you can see, it is generally seems in what at the means end of the supports, and the connection of slabs to the end of the beam will give you the L sections. So let's move to the steps 3 without wasting our time. So as you can see, it is similar process to that of the L sections. So in step 3 we will calculate design moment and the shear force. For design moment, we need to determine the loads acting on the sections, right? So first we have to calculate the means what you call load from slabs. As it is means L sections, it is monolithically constructed with the slab and the beam. So we have to calculate the self weight of the means slab. So self weight per meter length, right, for the per meter run. So as you know, its formula is B into D into rho, where the means B will be taken as 1, right? How much B will be taken for the 1? We will calculating for the 1 width, right? So B into, and the depth is 0.15 as it is 150 mm for 1 meter run, right, into density of concrete is nothing but the 20. So it will give you 3.75 kilonewton per meter square. So similarly, weight of floor finish we assumed 0.6. Live load is given 4 kilonewton per meter squares. So total all these load will be 8.35 kilonewton per meter square. As the beam is taking of 3.5 width of slab, right, as beam is taking 3.5 width of slab, right? Here if you have if you are not understanding these concepts, please go through the details of the flange beam, introduction of the flange beam. If you really understand this concept, then you can easily imagine all these things. My dear friends, I am requesting you, please watch that video so that you can understand this concept very clearly. So load on the beam from the slab will be, that is this load into this area into per meter. So ultimately the total load on the beam will be 25.05. so now we will calculate the load on reeve, right? That is load on weave. So the width of weave is given 300 mm from, we have already calculated in the above steps, that will be 0.3 meters. Depth of weave, right, that is depth of weave is nothing but these sections it is given as, totally it is given as, from topmost fiber to the, that is d minus 150, right? 150 is the thickness of, we need to subtract thickness of slab or the thickness of flange. So we will get 550 will be written as 0.55 meters. So for the, now for the self weight of reeve is nothing but the b into d into rho. So here the b is 0.3, d is 0.1, 0.55 and the density of concrete is 25. So ultimately we got 4.125, and we also need to calculate the plasters to the reeve. So we assume 0.5 kilonewton per meters. So the total load will be 25 these ones, right, and 4.125 these ones and 0.5 these ones. So total load that is acting on the L sections or the L beam is 29.675 kilonewton per meters. So means now we have already calculated the total load on the beam, so we can easily calculate the design moment, that is mu. Mu will be equal to W mu L square by 2L. So W mu will be, that is 29.675 into 1.5, that is factor load, right? So factor load will be this load into 1.5. So 1.5 into, here the effective length is given 8.3. So 8.3 squares divided by 12, you will get 255.583 kilonewtons meters. So similarly we will calculate shear force. Shear force formula is given W LE by 2. So here W similarly factor load, that is 29.67 into 1.5 into 8.3 divided by 2. So we will get 184.72 kilonewtons. It is similar steps that one of the vertical T beams. Now the difference is torsional moment. My dear friends, this is torsional moment at the support sections, right? As you know, at the supports the torsional moment will be acting. So as it is L sections, we have to calculate the extra torsional moment for the L sections. So the torsional moment is produced due to dead load of the slab and the live load of the slab, right? Because of these loads, the tear means what you call torsional moments are generating at that sections, at the support. So that is working load minus reeve self weight, and the working load is nothing but the means what is called factor load divided by 1.5. So 29.675 as it is calculated in the above, minus the means what you call weight of reeve, already we have calculated 4.125 in the above. So ultimately we got means what you call 25.55. So now we need to calculate ultimate load on the slab. So for the ultimate load means total load, right? Means for the whole effective length. Initially we have calculated for the per meter length. Now we will calculate for the whole effective length, that is for the 8.3. So for the means total means what you call ultimate load 1.5 as the factors into 25, right? 25 into 8.3 as the effective span or effective length. So ultimately we will get 318.09 kilonewton, right? So ultimate load. Similarly ultimate means shear force. So ultimate shear force will be W LE by 2. Here 1 by 2 W LE. So 1 by 2 will be 0.5, and the W into LE we have already calculated here. So we will just substitute this value, right? So 318. So similarly we got 159.045 as the ultimate shear force. So now we will calculate, we will see, right, as it is L sections, the distance of the centroid. Understand this concept, the distance of the centroid of the shear force, as shear force is acting right here, that is 159. We have already calculated above. Right now we have calculated 159 as it is acting at the center of the what you call width of flange, right? So the distance from the shear force from the center of the line of the beams, right? As it is beam, so center line of it is 300, so of course here to here will be 150, right? So the total from here to here is 41422, that is effective width of flange. So 1422 divided by 2 will give you the centers at where the shear force acting, right? Minus we have to take what you call centroidal of the shear force, that is at the mid of the shear, these ones. So this fully is 300, so minus 150, that is 300 divided by 2, so 571. So from these ones to here distance will be 571. So as you know, the torsion moment will be acting here, so TU will be 159.045, that is shear force into the distance, right, up to which the shear force will be acting. So 0.571, so 90.81 is the total ultimate torsional moment acting at the support. So let's calculate the next steps or the extra steps, means in compare of the T sections, that is equivalent bending moment and the shear force, right? This formula is given in page number 75 IS codebook 456. If you go in the page number 75, you will find all these formula. So at the supports, equivalent bending moment is compared as ME1 is equal to MU. As you know, the moment can be taken as, right, means moment through the torsions, right? So means a design moment plus moment through torsions. So let's calculate MT, right? So MT equal to TU, that is torsion into 1 plus D by B, right, by 1 means 1.7. So here the TU already we have calculated from the above equations, right? So here D is nothing but the overall depth is 750, so 0.75. B is width, so 0.3 we have taken at the width and 1.7. So if you do calculation, you will get 186.961 kilonewton per meters. So as you know, ME1 equal to MU plus M2. MU already we have calculated in the above equations, that is 255.538, plus here we have calculated MT. So MT will be 186.96. So ultimately you will get 442.49 kilonewton meter. So let's move to the here. Now we have calculated, now we need to calculate equivalent shear force, right? Equivalent shear force. We have calculated equivalent bending moment. Now we have to calculate equivalent shear force. So for the equivalent shear force, this formula will be given in the same page of IS codebook. So VE is equal to VU plus 1.6 TU by B. Here VU we have already calculated, that is shear force we have already calculated 184.72 plus 1.6. TU value we have calculated in the above 90.81. B is 300 0.3. So ultimately we got the equivalent shear force as 669.04 kilonewtons. So these are the extra steps which you need to be calculated in the L sections, as these are acting at the support. So now we will calculate the main longitudinal reinforcements similar to that of the vertical T sections. So at the means support is designed at the rectangulars to resist the hugging moment, right, or the hugging equivalent. So bending moment we have calculated is 442.49 kilonewtons. So we know that, my dear friends, we know the MU limit formula 0.36 FCK B XU max into D minus 0.42 XU max. So here 0.36 FCK is 20, B is 300, XU max can be calculated as 0.48 into 700, right? This value will be varying for the 250, for the 500, right? 0.48 is for FE 415, and this D is nothing but the what you call effective depth. As you know, XU max XU by, so this one, so D is nothing but 700 minus 0.42 into 0.48 into 700, right, this one. So if you do all this calculation, you will get 405.61 kilonewton per meters. So from these ones, as you can see, we need to calculate, now we need to calculate the area of reinforcement. For the area of reinforcement, equivalent bending moment is already we have calculated, right? So if you have the area means equivalent moment, what you call equivalent moment, then you can calculate it from the area of reinforcement from the here. So ME1 is equal to 0.87 FY AST D minus 0.42 XU. So means ME is 0. 442.49, and we need to take it into Newton mm. So for calculating kilonewtons meters into Newton mm, we have to multiply by 10 to the power 6. 0.87 as usual, Fy is 415, AST we need to calculate, right? So we have taken D in the means common, so we take it to D at the outside, so remaining 1 minus 0.42 XU by D. So as usual, this equation 0.87 into 415 into 700, and this AST as AST, right? And the D is 700 here, right? And 1 minus 0.42, and the XU formula will be given for the rectangle sections is 0.87 Fy AST, 0.36 FCK BD. This one is the formula for XU, that is neutral axis, for the rectangular sections, right? For the rectangular, right? So just we need to substitute all this value, and we have to calculate the AST value. So multiplying these ones, and I have take it out here, right? So similarly as equation 1 minus 0.42, 0.87 into 415, AST 0.36, 20 the FCK, B is 300, D is 700. So if you solve these ones, 1 minus 1.002 into 10 to the power minus 4 you will get. If you subtract with AST, you will form these equations, right? And after solving these equations, we got the value of AST as 2264.83 mm square. So this is the required value, right? So the number of bar can be determined as, that is capital AST by small ast. So capital AST, small ast can be calculated for the one. So we have assumed we are using 20 mm dia bar as the longitudinal reinforcement. So pi by 4 into 20, so we'll get 7.28. So we'll move to the even number. So 8 numbers of bar we are taking as the longitudinal reinforcement. So we assume 20 mm bar. So provide 8 numbers of bar as we calculated of 20 mm diameters in the longitudinal sections. So we need to calculate the actual AST. So pi by 4 into 20 squares as the diameter of bar, and how many numbers of bar we are using? 8 numbers of bar. So actual AST is 2513, right? Ultimately 2514. So we need to check whether this area of steel, actual area of steel, is correct or not. So for the A minimums, we got a formula right from the IS code book, 0.85 into BW into dy Fy. So will be is nothing but the 300, D is 700, Fy value is this one. So we got 430.1, which is less, right? So this value is greater, means this value is greater than this one. So design is okay. Let's calculate A max. So A max will be 4% of gross area, right? So 0.4 into B into capital D. So will get 90,000. So it is less than, it is what you call 90,000 is greater than this one. So we can say that this value actual which we have calculated for the actual AST is correct, means check is, or the design is going in the okay manner. Now for the steps 6 we will going to calculate. My dear friends, in what you call L sections, we need to calculate the side face reinforcement also, right? In the once I will show you the detailing of the diagrams, you will going to understand. So for the side faces reinforced, we need to calculate. And this, why you need to calculate the side face reinforced? As we know, for the L sections member, it is subjected with the torsions, right? So due to the torsions, we need to provide extra bar to prevent from the failure, right? As it means at the supports, the torsions is acting, so torsion moment is acting, so we have to prevent from all these actions. So we have to provide the extra bar as the side face. So for that, once it is given in code book that we need to provide a steel reinforcement in the side side face 0.1% of weave area, right? 0.1% of weave area. So 0.1% is nothing but 0.00, that is 0.1 divided by, as it is 0.1 divided by 100, so 0.001 into B. B is nothing but the 300 into D. D is 750, so 225. So in the 225, we need to calculate the number of, means how many numbers of bar we are going to insert in it. So capital AST by small ast, capital AST we have already calculated, small ast we will provide, we will assume that we will going to provide 10 mm dia bar. So pi by 4, so ultimately we will get the answers 2.86. So we can't take 3 as it is the even, so we will go through the odd. So 4 numbers of bar we are going to provide as the side face reinforcement in the L sections. So let's move to the another steps. So here you can provide 10 mm bar of the 4 numbers. So in steps 7 we'll calculate the shear reinforcement as that of the what you call T sections, right? So shear reinforcement for we need to calculate equivalent, means vertical equivalent nominal shear stress will be given as VE by BWD. V is we have already calculated, that is 669.41 kilonewtons. We have to take it into newtons, so into 10 to the power 3. BW is 300. It is already given, or we have calculated in the above. So D is nothing but the 700 effective depth. So that means we got is means 3.18, right, Newton. Here will be Newton per mm square. So we have to calculate the percentage of steel, right? So for the percentage of steel, AST divided by BWT into 100. So AST is nothing but the actual AST. So actual AST value is 2514 divided by 300 into 700 into 100. So we will take means 1.197, as it can be also written as 2%. So we have to check means vertical table of page number 73 for the 2% of steels, what will be the tau c value. So let's move to the page number 73 of IS codebook. Yes, as you can see here, my dear friends, for what equals 2%, as you can see, M20 for M20 is nothing but the same 0.79. If the exact value does not match with these ones, then we have to go through the interpolation method, right? We have to take, if the suppose if the value lies between these ones, then we have to go through the interpolation methods, and I have explained the interpolation methods in the design of singly reinforced beam. So if you really want to know, then please go through that video so that you can understand how to do interpolations methods of solving these ones. So for the 2% we got tau c value 0.79 Newton per mm square. As from the above we can see that tau bc is greater than tau c, so we have to go through the shear reinforce required. The shear reinforce is nothing but the providing of stirrups in the design. So let's provide the stirrups in the designs. So we will assume we are going to provide 10 mm diameter stirrups, right? So my dear friends, while we provide the stirrups, we have to subtract 25 mm from the top and bottoms, right, in the L sections. So while we subtract means 25 mm from the top and bottom, so the B1 will be 250, right, because 25 50, so 300 minus 50 will get 250. So SB for the what you call L sections will be given as 0.87 into Fy into ASB into D1s by TU by B1 plus BU by 2.5. So we will substitute all these value. We have each and every value. Fy is 415, ASB will be the pi by 4 into area. How much diameter we have taken? 10 into 2, because it is 2-legged vertical stirrups, and I have explained you what do you mean by 2-legged vertical stirrups. The stirrups which are using generally, right, in the means normal residential constructions is nothing but the 2-legged vertical stirrups. And this one's D will be means 700 minus 25 minus 25, it will be 650, right. Similarly TU value we have already calculated, right, VU value we have already calculated, right. After doing all these things we will get as means 84.9. so by doing round of it, as it is very less small, means it is very what you call less small, so we have taken it as 160 mm. So my dear friends, we will provide means stirrups means distance 160 mm at or near the supports, and at the mid of the spans we will going to at the 300 mm center to centers. So hope you understand this one. So let's understand if this one is sections. So here as you can see, it is 10 mm diameter of stirrups and 160 mm center to centers. The distance of the two stirrups here is less because the shear torsion force are acting at near the center of the support. So to prevent from the failures, we need to provide the stirrups of the less spans, means less distance. At the mid, as you can see, means what you call 300 mm center to centers, right, of 10 mm dia, right. This one's where the 8 number of bar is provided. This one is 8 as the clear span. The support is 300 and the support is 300. This is L sections. My dear friends, we have provided 3 numbers of bar at the top and the 8 number of bars at the bottoms. We have already calculated. Hence, see, this one is the side face reinforcement. So we provide these ones to prevent from the torsions. So this one is 1 2 3 4, we have provided 4 numbers of means vertical face means side face reinforced, right, of 10 mm diameters. This one's the total depth is 750. So hope you understand this concept and means the work design of L sections. If you really like my video, please don't forget to subscribe, share it to your friends. So thank you for your times and take care of yourself. Bye bye.